Hello guys, how you doing? Today is the last session of chapter 4 of Fluid Mechanics 1. I'm really excited that you have accompanied me till here, and I'll be so much delighted if you accompany me till end of this video, which is having the subject of the Reynolds transfer theorem. So follow me with the whole video. So before going on instruction, I'm going to introduce you one more time the subject and also introduce myself. The subject is the Reynolds transfer theorem from section 4.4 of chapter 4 of Fluid Mechanics 1. My name is Amir Reza Talagat with the email address of amirrezatalagat@gmail.com. Please don't hesitate to ask your questions. You can just provide them in the comments or in the email. I'll try my best to give you the answers as soon as possible. So, in the previous chapter, we tried to identify the fluid motions in the interest of two methods, Euler and Lagrangian method. Here we want to know what's going to be happening in the particular part of the fluid and what's the effect of that particular part of the fluid on the volume or on the object. In here we need to describe the governing fluid motions in both system concepts, which are system and the control volume. There's a connection between these two, system and the control volume, which is going to be using tool as Reynolds transfer theorem, which is going to describe the physical parameters such as velocity, acceleration, mass, temperature, and the momentum. In further steps, we can just attribute a parameter capital B, which is representing all of these parameters, and a small b, which is defined the capital B per unit of mass. For example, here we have the momentum as momentum equation as m multiplied by v. If we divide it by a unit of mass, we can have it as a capital V in here, which is the attribute which is corresponded to the capital B in here. Or on the other example, we have it as a kinetic energy, which is half of mv to power 2. If we divide it by a small m, it means per unit of mass, we have the small unit of b, 1/2 of v to power 2. So the term B, it's regarded as an extensive property in every fluid. If we divide it by, per unit of mass, if we have it as a per unit of mass, it's going to be described as the intensive property. Excuse me. As you can already see, capital B is dependent to the mass. However, the small one is independent, which means the capital B is the adding up the amount of associated of each fluid particle. If we want to have it as the collection of every particle, we have to describe it as integral or limitational mathematical limit and limitation, as well as the integral mathematical concept, which is written as here. We have the small b rho delta v, which is m, a small m. If we have a time rate of change of every parameter, every b parameter in a whole system, we have it as this equation 4.8, which is the time rate of change of parameter b in a system as the integral term here. On the control volume, there is just a change in the limitation, which is CV in here. as you see in here, there's the CV limitation for the control volume, and the SYS is the standing for system. Yes, yeah. The only difference between equation 4.8 and the 4.9 is the term which I'm going to illustrate about it in further steps, which is somehow the convective terms. Another thing is that the control volume is defining and introducing a space, which is not having to do with the details of the particle. However, the mass is dealing with the details of the particle, such as mass, density, and something like that. There are, in some instance, the control volume and the system are going to occupy the same volume in space momentarily. Despite this, it doesn't mean the time rate of change of parameter B in a system is identical with the corresponding one in the control volume. The Reynolds transport theorem is going to illustrate it to us in more detail. Here we have, let me just match it. Yeah. Here we have an example which I'm going to solve it for you in a handwritten text, which is about time rate of change for a system and a control volume. As I illustrated to you before, the difference between the control volume and the system is very obvious, but in calculation it is so much important to be regarded. Here I'm going to solve you the example 4.7. So follow me with the written text. So here we have the example 4.7, which is about time rate of change of system and control volume, which is from section 4.4 of chapter 4. The question wants us to determine the difference between dB of the system over dt and dB of the control volume over dt if the B represents the mass, which is about the fluid flowing from an extinguisher tank shown in figure E4.7a. If we just regard the B is equal to the mass, the system, the B in the small b is going to be equal to 1 because it's per unit of mass. And the equations 4.8 and 4.9 could be written as dB of the system over dt is equal to dm small of the system over dt, which is equal to d of integration over the system rho total v divided by dt. And for the equation 9 we have the dB of the control volume over dt, which is going to be equal to dm of control v dt, which is equal to the integration of the control volume rho dv over dt. You know, these two are representing the time rate of change of mass within the system as well as the control volume. If we choose the system such that the fluid within the tank at the same time as figure E.47, if we just open the valve at a time more than t equal to 0, the fluid is going to be going out, which means the d over control volume of rho dv over dt is going to be less than 0 because it's decreasing the it's having the deterioration of the fluid particles. However, at the other side, the control and the system is going to be remain the same because we have the conservation of the mass regarded. And the limits of the system and the control volume are at an instant are the same, and they don't change after the decrease in the gas of the extinguisher tank. So, but there are some times that d of control d over integration of control volume of rho dv over t dt is less than d of integration over system rho dv over dt, and sometimes bigger than equal. It depends on the situation that we are considering. Welcome back, guys. Here, I'm going to illustrate some principles about the derivations of Reynolds transport theorem. Let's take a variable area duct section as an example. In the time t, we have the control volume and the system completely identical. They are in the same position and same situation. As the time passes by delta t, we have it as this. Take a look at here. The control volume is changing in position. It's having the position of region 2, which is comprised as some part, pay attention, some part of the previous situation, which is control control volume minus the region 1, and the new position, which is regarded as this. So in a new situation, which is passed by delta t time, t plus delta t, we have the situation of control volume minus the region 1 plus the region 2 at time t plus delta t. So here we have it as this. As I told you, in time t, the parameter b at the system is equal with the corresponding one in the control volume. As the time passes by, it's going to be changing. If we want to have the changing in time of parameter b in a system, we have it as b sys as in time t plus delta t minus b sys at t divided by delta t. It's the time change of parameter in system at the time duration. It is written as b of control volume at time plus delta t minus the same duration at b1 at the region 1 plus that happening in the region 2 minus the original situation. If we take a look at equation 4.10, we can reduce this, we can have a changing of this equation to this. This part is the is illustrating the time deviation. This part is somehow a convective terms and unsteady terms. I'm going to illustrate it to you in further slides. As you see, the moving system flows through a fixed control volume by defining this equation. Interesting thing about equation 4.10 it is that somehow it is it is completely pointing to the material derivative of the parameter, which means we can have the equation of 4.10 as the time derivative. So it means that the Reynolds transport theorem is the fluid mechanical concept of material derivative. Take it as an example for quantity of pressure. It is representing the time rate of change of quantity of pressure at the given particular fluid at specific time as it moves along. So in the same concept, we can have the B parameter as representing the time rate of change of parameter B in a particular fluid as it moves along. So we can write it as equation 4.11 in an integral term. Another interesting thing that we can have in the equation let me just illustrate it in the next slide. Yeah. When we are having a volume, it is comprised of cross-sectional area in a longitude. At a longitude, it is already defined as the velocity in a time duration. So we can have it as this. By now, we know that B multiplied by delta V is M, is small m. Excuse me, rho multiplied by delta V is a small m, which is going to be multiplied by small b to have the capital B. Having the volume, we can write it as V velocity multiplied by time, which V multiplied by time is the longitude. AL is going to be gained as the volume. Doing the whole calculation and having the limitational calculation for the parameter B, we can reach to the equations of 4.14 and 4.15. It is somehow illustrating that the derivative, the material derivative of parameter B is comprised of the rate of change of parameter B in the control volume plus the total flow that's going in the control volume and minus which is getting out of the control volume. And also based on once again based on equation 4.15, it's already pointing that the time rate of change in the system for the parameter B is not always the same for that happening in the control volume. The time rate of change of a system property is the Lagrangian concept, is as I have already illustrated to you. So here we have example 4.8, which is about use of Reynolds transport theorem. I'm going to solve it for you in a written text. So follow me with the written text. So here we have the last example of this chapter, which is about the use of the Reynolds transport theorem from section 4.4 of chapter 4. The question is, consider again the flow from the extinguisher shown in figure E4.7. Let the extensive property of interest be the system mass, B equal to M, or B is equal to 1. Write the appropriate form of Reynolds transport theorem for this flow. So, as you see in the figure E4.7, we don't have any inlet. we just need to take the control volume of the fire extinguisher and system in a fluid of a system of the fluid within the time 0 the same. So at time equal to 0, system and control volume are the same. As we don't have any inlet, we just need to take the consideration of the outside. So a combination of equations 4.15 and equation 4.9 is going to be giving us as d over system divided by dt is gonna be equal to round of integration over control volume of rho dv over dt plus rho 2 a2 v2. Welcome back, guys. As I already told you, we can simplify this system and the control volume and relating to them with the Reynolds transfer theorem. However, sometimes it's not really easy to do that. Taking the heart as an example, it's regarded as a control volume. Having the same analysis on the fluid which are going through the lungs and the arteries in the heart, it's not somehow an easy performance. In this picture, you can see how we can apply the Reynolds transfer theorem and having the same calculations in a pipes. We can just we just need to consider the inlets and the outlets and having the sufficient and appropriate control volume regarding to them. We just need to repeat the previous steps by through which we identified the time derivative of parameter b in a system. Guys, here is really important subject. When we are considering a control volume, there is an inlet and outlet. Inlet and outlet are going to be distinguished by an interface through the whole control volume. That interface is the control surface. When it is getting out or when it's getting in, we have a control surface. Sometimes velocity through this surface is not in the same in the same direction with the normal of that surface. It's having a corresponding angle. So we have to image it such that it's going to somehow it lies on the vector of normal of the control surface. We can do it by the triangular equations as cosine theta. As you see in here, when we are going to identify the delta b, we have it as small b rho delta v, which is small m. Delta v itself is comprised once again as delta a multiplied by delta l. Delta l itself, by having the image concept of the velocity on the normal vector of the control surface, is going to be as v cosine theta delta t. V delta t is itself is delta l, excuse me. When we want to image it, we have to multiply by cosine theta. Having the time derivation, we can have the time rate of change of parameter b in the corresponding system. If we just providing that, we multiply it by cosine theta, we can have the total complete equation as this: rho v cosine theta delta a. Here I'm going to illustrate to you how is the derivation of Reynolds transport theorem is going to be applied in the mathematical calculation. As you know, we have the cosine theta in the equation, which means that if we have an angle, the cosine calculation is going to affect the sign of the integral. In the inflow, in the inlet interface, the flow is going this way. However, the normal vector of the control surface is in the opposite direction, which means the theta is 180. So the cosine of it is going to be -1. In the outlet, the normal surface is in the same direction with the flow. So the cosine is 0, which is positive. Here is another illustration. Whenever the theta is between -90 and +90, the cosine is having the positive sign. On the other hand, when the angle is between 90 and 270, the cosine sign is going to be negative. There is a specific situation that might be happening, which is in the top. In the top, there is two corresponding situations. One, when the velocity or the cosine theta are going to be equal to 0. V equal to 0, it means that fluid is sticking to the surface. On the other, and furthermore, the cosine theta is equal to 0 whenever the fluid is sliding along the surface without crossing it, as it's illustrated in here. Doing the whole calculation, we can have the material derivative, or in other words, the Reynolds transfer theorem for the parameter B in a system as time rate of change of a parameter B in a control volume plus the total flow, which is getting in, which is getting out, minus which is getting in. It's illustrated in equation 4.19. Once again, in a same concept, we can have the example of this control surface. When you go to the bathroom, you can use this element. By having the same imagination and assumption about what we have already instructed about the Taylor's transport theorem, you can have the physical interpretation of this concept. Here once again has pointed to the relation between material derivative of the parameter B and the Reynolds transport theorem. The time derivative is pointing to the time effects on the control volume. On the other side, the time which is in integral of the control surface is pointing to the convective terms. All in all, the connection between Reynolds transport theorem and the material derivative is the same concept of utilizing the Lagrangian method heading to the Eulerian method. In other words, we can just describe the fluid motions by having the Lagrangian method, and at the end we can transport it to the Eulerian method by Reynolds transport theorem. There is a specific cases. There are specific cases. If we have a steady state situation, it means time duration, it's not having any effect on the Reynolds transport theorem. So the first part of it, which is relating to the control volume, is going to be omitted automatically, which we can have it as equation 4.20. Equation 4.20 is also pointing to one more thing. It means that whether or not we have a steady state situation, on a steady flow or something like that, there's one particular situation which is a steady state as well as a steady flow. But in other cases, there is not any situation such that the material derivative of the parameter b in a system is going to be 0. So, as illustrated in this part, we cannot always have the material derivative of parameter b in a system equal to 0. However, in chapter 5, I'm going to illustrate with one specific situation which is going to be 0. But in other cases, it's not 0. Because when we have the conservation of mass, which is going to be illustrated in chapter 5, it is going to be 0. But when we are considering for momentum equation, it is going to be seen that it's the right side of the equation 4.9, which is here, is not 0. Let's have a special situation. We have an unsteady situation, but we have a steady flow. When we have a steady flow, it could be happening by the constant diameter or constant flow of the fluid. Here we have a constant diameter of the pipe, which is relating to the constant area in an unsteady state. When we have a steady flow by regarding the assumption of constant area, if we have the equation of momentum, which is mb, the small b is just velocity because it's per unit of mass. Applying it in equation 4.19, we can have it in the inlet as well as the outlet. In the inlet, because the cosine is 180, we have the minus sign as here. At the outlet, we have the positive sign. Having the combination of them, it's going to be 0. However, once we have unsteady effects, the time derivative in the control volume, in order to calculate the time derivative of parameter b, is going to be regarded. There is an unsteady effect in the second situation. Once we have a variable area, as you see, the area has varied in here, which means we have the convective terms existing. Another unsteady effect is when we have a moving control volume as this, which means we have two velocities. One, the absolute velocity, and another one is control volume velocity. The difference between the control volume velocity and absolute velocity is gained by having the relative velocity, which is illustrated in equation 4.22. The relative velocity is the velocity which is seen by the observer passing on the control volume. Take the passenger in the airplane as an example. Well, once he's looking at the engine of that airplane, he's sensing relative velocity. When the airplane is passing by in the sky from an identified origin, it's having the the control volume velocity. An observer on the ground who sees the airplane is just having the concept of the absolute velocity. Another example is this. The velocity of the water nozzle is 100 feet per second, and the vane, which is control volume, is 20 feet per second. We can have the relative velocity as 100 minus 20, which is 80 feet per second. Having the same concepts about material derivative and the Reynolds transport theorem in the moving control volume, we just have to replace the relative velocity in the equation 4.19, which is here. Excuse me, which is here. We just have to take place of the relative velocity for the moving control volume. Yeah. All in all, when we want to describe the forces which are exerting on a body, we have to draw the free body diagrams. In the fluid mechanical concept, we're doing the same thing by identifying the control volume and having study about the forces which are exerting on the control volume. It means we have to introduce the control volume in a realistic way such that we can calculate. In other words, we have to take the point on the limits of the control surface in the inlet and the outlet because of two reasons. One, because the point is in the limits, which we can identify the situations in the limits, and also the point in the control surface is normal to the direction of the flow. It means we can have the better calculation in the Reynolds transport theorem. So this is the end of this session. I hope you have accompanied me till here and also grasp the concepts. I'm really glad that you have seen the whole video. Please don't hesitate to ask your questions. I try my best to give you the answer as soon as possible. You can just provide them in the comment or in the email. Once again, I really suggest you to subscribe the channel in order to get the notification of all upcoming instructional sessions. See you in the next chapter. I bid you all farewell. Excuse me, do you want to use here? No, 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 no. Ooh.